Hello everyone and welcome to this webinar of the Future Tech Week about the CompInnova project. My name is Luca Zanotti Fragonara and I'm a senior lecturer at Cranfield University. CompInnova is a project about a novel approach for the autonomous inspection and repair of aircraft composite structures. My presentation will shortly introduce the background to the project, the partners of the project, our objectives, and give you a brief project overview before having a presentation from each one of our partners. Let us start with a bit of background about the CompInnova project. The background is in the framework of aircraft maintenance checks and how long they last and how often they are carried out. This is strongly affected by the way that aircraft are aging. Aircraft, in fact, do not age just like humans with calendar days, but they also age by flight hours and how long the aircraft has flown, and also by flight cycles. Flight cycles are measured in terms of takeoff and landings that an aircraft has carried out. Let us have a look to the four types of aircraft maintenance checks that exist in the civil aviation. A, B, C, and D checks. From the less detailed check to the most detailed check. A checks are typically carried out every 120-150 hours, and they are mostly visual examination of structural components, the power plant, avionics, and some accessories. To give you an idea, the duration of the A checks on average is about 8 hours of ground time and 60 man-hours. B checks are a bit more detailed and carried out a bit less often, and they are every 750 flight hours. They are basically entailing everything that is carried out during an A check plus some other operational checks and some open inspection of panels. This requires 24 hours of ground time and about 200 man-hours of work. C checks and D checks are the one that CompInnova is mostly looking at. They are carried out every 3,000 flight hours, and they are entailing all the operation of A and B checks, plus a very detailed inspection of the airframe, the engines, and accessories. Also, flight controls are calibrated. For what concerns C checks, we have 72 hours of ground time on average and 3,000 man-hours of work. D checks, again, they are carried out every 20,000 flight hours. They are the most detailed checks that an aircraft can go through, and they include the removal of cabin interiors to allow a detailed structural inspection in order to carry out NDT on basically all components of an aircraft. Some components are even completely replaced. This requires 21 days of ground time and 10,000 man-hours of work. To give you an idea of the context, the whole aerospace maintenance, repair and operation sector was valued at about $75 billion in 2018. To have a comparison, the aerospace composites market alone is estimated at $20 billion in 2018. So you understand that the MRO sector is huge in terms of value. Currently, not all the components of the MRO sector entail composite aircraft, because we have some old and mid-generation aircraft that are still in operation, as you can see from the graph. This quota of new generation aircraft that are mostly built in composite anyway is growing and growing in the last years. Aviation is changing, and it's changing because of the new digital technology and the new digital systems that are being currently integrated on the pre-existing technologies. You may have heard of technologies such as the one of the conscious aircraft, where self-monitoring and self-learning are enabled by techniques such as artificial intelligence and machine learning. In this context, we have also other technologies like robotics and autonomy that can play an important role in the area of aircraft maintenance. In Cranfield, we created a new research center that is called the Digital Aviation Research Center, DARTEC, and I invite you to consult our white paper about addressing the digital aviation challenge. In this context, what is the future of MRO? For instance, this is an interesting concept proposed by Airbus, which is the hangar of the future demonstrator. This entails data storage, predictive maintenance, but also automated inspection and data collection using UAVs and autonomous robots. CompInnova is about this, is about making this become a reality, making robots and new technologies to collect data integrated in a much more complex system that is the hangar of the future. So, in this context, what is the CompInnova concept? The CompInnova concept is about the integration on a mobile vortex robot inspector that is able of climbing on the fuselage and on a wing of an aircraft composite structure that does not allow magnetic wheels, of two different NDT techniques that allow us to understand the status of the structure. The two techniques are phased array ultrasonic and infrared thermography. The advantage of these techniques is that they both produce images that can be easily fused in an integrated software. Finally, once a defect or a damage is detected and sized by the inspectors, we have developed also an innovative repair system that is able to automatically repair the damage in the composite structure. In terms of overall project aim and objectives, we want to develop an automated NDT approach that is capable of detecting, evaluating, and repairing damages on composite aircraft components. So we have 4 different specific objectives developed by each one of the partners about development of a novel climbing robot technology for the autonomous inspection of composite aerospace structures, the development of a novel infrared thermography approach for the fast and quantitative automated file inspection of damage in aircraft composites, the development of a phase array ultrasonic module for the inspection of aircraft composite structures with minimizing the water coupling, and finally, the development of an automated laser repair strategy and of a digital twin model. So who's member of the CompInnova Consortium? I'm going to introduce the partner with the same order of the webinar of today. The first partner is the University of Ioannina in Greece, who developed the thermography and NDT technology. Then we will have a talk from Cranfield University, who developed the phase array and NDT technology and also was the project coordinator. University of Patras in Greece, who developed the automated repair technology and also developed the digital twinning. Luleå University of Technology from Sweden, who developed the Vortex robotic platform. And finally, we have Optimal Structural Solution, which is an industry and helped and assisted the consortium in developing the prototype of the composite sample that was used throughout the project and provided a validation of the technology from an industrial point of view. So, thank you very much for listening to this brief introduction and project overview, and I hope you are going to enjoy the rest of the webinar with our project partners.